Hi everyone. Hopefully you're enjoying your time at home. Today I'll be going through the questions in the revision booklet that has been posted up onto Google Classroom. Just a few notes before we begin. I will be posting up this particular PDF that I've written all over onto the Google Classroom, so don't feel like you need to take notes. But if you would like to, that's okay too. And another note about the source of these questions, you'll find the first half of this booklet online on a site called Learnable Electromagnetism. I've taken a few questions from that site, not all of them. So if you feel like you want a bit more of a challenge, feel free to go up there too. The other half, the later half of this booklet is from last year's 2019 HSC exam for physics. And I haven't taken all of the electromagnetism questions from that exam. So there are still a couple that I've missed. So if you'd like to go back to last year's exam and attempt those questions for extra revision, I encourage you to do so. But without further ado, let us begin. So, uh, looking at the very first question, we see that this is a case of parallel current carrying conductors. We're told that these three parallel conductors, they carry the same current, as we can see here. Okay, I. And P and Q here are fixed in place, and the magnitude of the force between the conductors Q and R, so these two on the left here, on the right here, the force between them is F newtons. And so let me draw that in, like so. We know that this is going to be a repulsive force, because the currents are flowing in opposite directions, as we can see here, right? So if they're flowing in opposite directions, we have a repulsive force. And if they're flowing, as you guessed it, in the same direction, then there is an attractive force. And so the question asks us, what is the net force on conductor P when it's in the position shown? And so let's have a look at conductor P. So conductor P is going to experience two forces. One is going to be from conductor Q, and the other one is going to be from conductor R. Okay, and so let's focus on one at a time. So let's focus on the force that's going to be placed on P by Q. So if we compare P and Q, we notice that the currents are flowing in opposite directions, which means that there's going to be a repulsive force away from P. Okay, so there's going to be a force on P in this direction. And what is the magnitude of this force? Well, remember we're told that the force between Q and R is F. And we notice that the distance between Q and R is 10 millimeters. And we have the same currents. And so if we were to just think about, well, what is the force then on current carrying conductor P? It's going to be the exact same force because it's separated by the same distance here, 10 millimeters, and it's also got the same current in Q and P. And so really it's no different from this scenario here. And so we know that this is going to be F. Now let's think about the force on conductor P by conductor R. Okay, so remember we said that FQ here is F, yeah? The force placed on P by Q is F, but now what is the force placed on P by R? So if we compare conductor P and R, what's the direction of the currents? Are they in the same direction or the opposite direction? Well, we see that they're in the same direction, which means there's going to be an attractive force. And so really the force is going to point in this direction. It's going to point towards R, right? And now what is the magnitude of this force? Well, we notice that the distance separating P and R is actually double. It's actually 20 millimeters, isn't it? It's 20. And so it's actually double the distance away. And so my question is, well, if a conductor is further away, will it experience a stronger force or a weaker force? Will this attractive force be weaker than F or stronger than F? Well, if it's further away, intuitively, hopefully, it's actually weaker. Okay, and so it's going to be weaker by how much? Well, actually by a factor of 2. And how do we know this? Well, if you consult your formula sheet, you'll notice that the formula that concerns this particular situation looks sort of like this. You have your 2 pi r here, and you have your I1 and your I2. So remember that mu naught and 2 pi are just constants. R is what we're concerned about. R is the distance between the conductors, okay? And so we notice that, well, it's not squared, it's just a linear R, okay? And so that means it's going to be, the force is going to be directly linearly, inversely proportional to the distance. And so therefore, FR is going to be exactly F on 2. Okay, and so if we sum these forces up, we notice that if this over here, let me just correct this now. If this is F, sorry, and this over here, this force over here is F on 2, we now have a sum. We need to sum this force, which is F, and that force, which is F on 2. And so the total net force is actually going to be F on 2 newtons to the left. And so therefore, the answer to question 1 is A. Let's move on. In this question, we're given a motor setup. We notice we've got our 2 bar magnets on the left and the right here. They set up this magnetic field going towards the right. And we've got a coil. Now we're looking at this coil in a funny way. Current isn't flowing like this, but really it's actually flowing into the page here, and it's flowing out of the page here. Okay, that's what the current is doing. And then we notice that we're given 2 equations. We're given the torque equation. Here's the torque for your motor. And we're also given F equals ILB. And hopefully that rings a bell. That's actually the motor effect. That's the force due to the motor effect. And then the question asks us, what are the angles theta and phi in the above equations? And so let's take it one by one. In the motor effect, let's start with this one over here. In the motor effect, okay, let me write it down. F equals, so maybe over here, phi. What is phi in the motor effect? Well, if we remember back to our classic example where we have a current carrying conductor here, and we've got a magnetic field surrounding this current carrying conductor, we know that because of the right-hand palm rule, if you point your thumb in the direction of the current and your fingers into the page because of the magnetic field, sorry, I forgot to label this, you will know that there's a force pointing towards the left on this current carrying conductor. There'll be a force. And this force is because of the motor effect, okay? Well, what we're concerned with is phi. What about the sine phi at the end? Well, what is phi in this particular example? In this example over here, phi is 90 degrees. That's because phi is the angle, it's the angle between the conductor and the direction of the magnetic field. Let me just write this. And so if we notice over here in the question now, the current is actually going into the page here. Let's forget about this side and let's just focus on the part of the current going into the page. The current is going into the page, or in other words, the conductor is going into the page. And the magnetic field is, let me show you, is pointing in this direction, isn't it? That's the magnetic field. And so my question is, what's the angle between the magnetic field and the conductor? Well, if you point your finger into the page, and then you point another finger to the right, and I encourage you to do this, you'll notice that the angle is actually 90 degrees. It's perpendicular. And so the answer here for phi has to be 90. And so we notice that B and D cannot be correct. And so therefore only A and C could be correct. And so now let's have a look at theta. Theta in the torque equation, what is it? Well, if we look at theta in this equation, theta is actually the angle between the normal of the coil and, again, the direction of the B field or of the magnetic field. Okay, so let's take this slow. Let's have a look at what this means. It's angle between the normal of the coil. Okay, so let me rub this out for a minute. What is the normal of the coil? Well, what it's talking about is if you take the plane of the coil and you draw a normal to it, this is what it looks like. This is the normal of the coil. Now it's the angle between that line and the direction of the magnetic field. Well, again, let me draw in the direction of the magnetic field. The magnetic field looks like this. And so it's asking us, well, what is this angle? That's theta. And how do we find this out? Well, if we look at this diagram, we know that the coil makes an angle of 30 degrees with the direction of the magnetic field here. And so we know that this angle over here must be 90 because remember this is a normal. And so that leaves us clearly that theta here must be 60 degrees because this is a straight line. This is a straight line over here. And so 180 minus 90 minus 30 must be 60. And so therefore what we have as the answer must be C. And so the answer here is C, where theta is equal to 60 and phi is equal to 90. All right. Here it looks like we're continuing on, and this is a question that's more focused on the motor effect. Okay, so you got to keep the motor effect fresh in your brains. And what we're given is a DC motor, because we see that there's a split ring commutator over here. And it gives us a lot of information, and I assume we'll be doing some calculations afterwards, yes. And so part A asks us to describe the role of the commutator. Well, very quickly, we know that the role of the split ring commutator is actually to reverse the direction of current. And it does this every half turn or every half cycle. All right. Now, that if you just wrote that, that won't give you full marks, actually. You need to sort of answer the question, well, so what? Why does it do this? Why does it reverse the direction of current every half turn? Give me a reason, right? Well, why do we reverse the direction of current every half turn? It's actually to ensure that the torque is in the same direction, right? You want to maintain the torque in the same direction. Or in other words, what am I really saying? I'm really saying that I want the motor to continue rotating in the same way, right? I don't want the torque to suddenly reverse, okay? And so this, in reality, you should say, ensures the motor continues to spin in the same direction. Oh. Okay, part B. Calculate the magnitude. So here we've got the magnitude and direction, a lot of people forget this, of the maximum torque produced by the DC motor. And the key word here is the maximum torque. And so if we look up here at this diagram, is this already in the maximum torque position? Well, remember our torque equation over here is T is equal to NIAB sine of theta. Now, when is theta maximum? Or sine theta maximum? Well, sine theta maximum value is 1. And for sine theta to equal to 1, theta must equal to 90. Now, my question is, in this case over here, in this diagram, is theta already 90? Well, let's think about what theta is again. Theta is the normal, so in other words, going straight up, it's the normal to the plane of the coil. Theta is the angle between the normal and the direction of the magnetic field. And so here, this angle is 90. And so therefore, this coil already is in the maximum torque position. And so we just need to sort of fill in the values here, okay? Let's all write down the values that the question gives us. It gives us 100 turns of wire. So here, N is 100. It gives us that the area is going to be 0.2 times 0.1 meters. And that's already in SI units for us, conveniently. So all I need to do is multiply the two numbers, and I'll get 0.02. I also get that the magnetic field in this coil is 0.02, if I just quickly do the scientific notation. And the current that we're given is 4 amps. Okay? And so all we need to do now is just quickly to substitute all these values into our torque equation. And so we get that torque is equal to 100 multiplied by 4 multiplied by 0.02 multiplied by 0.02 again times sine of 90 degrees. Okay? And you will find that if I quickly pull out my calculator, that 100 times 4 times 0.02 times 0.02 is equal to 0.16. And remember, the units for torque is Newton meters. And so that is part B, right here. All right, for part C, let's have a look at part C. It says a mass is attached to the coil to prevent it from rotating. Which side of the coil, A, B, or DC, should the mass be attached, and hence calculate the mass? Okay, so this is asking us, when the motor starts rotating, we want to hang a mass to stop it from rotating. And so we need to figure out which direction is it going to start rotating. And so if you look at this part of the coil, let's focus on this side of the coil here. What happens when this side of the coil, what happens when the current, well, what direction is the current flowing in this side of the coil? It's flowing in this direction, isn't it? In this direction. That's the direction of the current. And then this is the direction of the magnetic field, right? And so if you use your right-hand palm rule, you'll realize that this side of the coil over here, AB, is going to be pushed downwards. Is that correct? No, it's going to be pushed upwards. Yes. It's going to be pushed upwards, right? So this part of the coil is going to go up. Okay? And CD is going to go down. Okay? And so the coil is going to rotate in that direction. AB is going to move up, CD is going to move down. And so which side should we attach it to? Well, clearly, in order to stop AB from moving up, we're going to hang a mass on AB, right? So the answer is AB here. And we want to calculate the mass, okay? And so remember, we're just hanging it. And so the mass here, if I were to draw, let's draw AB. Let's say this is the coil A, or the side of the coil AB. And we've got the force due to the motor effect up here. So, yeah. And then we've got another force from the mass, which is mg, and we want it to balance, right? To be exactly equal so that AB doesn't move, okay? So that's Newton's, Newton's first law, okay? We want the forces to be balanced. We want the net force to be 0. And so in other words, mg is equal to BIL sine phi. Okay, or in other words, it's really just equal to BIL because here phi is equal to 90 degrees. How do I know this? Well, remember phi is the angle between, for Bill, remember, for BIL sine theta, phi is the angle between the direction of the magnetic field, which is what we see here, and the direction of the current. Yeah? And so really what we see here is that that's 90. And so really phi is 90 here. And so mg is equal to BIL. And remember, B is 2. Oh, not 2, sorry. 0.02. L, what is L? Oh, I, sorry. I is 4. And what is L? L is the length of the conductor AB. And tells us that AB is 0.2 meters. And so it's 0.2. And then we have M, which is what we're trying to find out, and we've got 9.8 over here. And so really, M is just equal to this business up the top here, divided by 9.8. And so if I type that into the calculator, I will get 0. Give me a second. I will get 0.0016, and this is in mass, and so that's kilograms. All right, for the last part of the question, a student suggests the following improvements for increasing the speed of the rotation of the coil, and it asks us to justify the suggestions. So for part D, it tells us to, the student tells us, or suggests, to replace the single coil over here, this singular coil, right, with several turns. Okay. Well, what does it mean? Well, if we want to have it have, more turns, what it really is suggesting is that it has, so let's have a look up here. It says this motor already consists of 100 turns of wire. So obviously if it is replaced with a coil with several turns, then that means it's going to directly increase the torque, because torque is proportional to the number of turns. Or we know this because it's in the formula, isn't it? And what happens when we replace the permanent plane magnets with radial magnets? Okay, so remember, radial magnets aren't these block-looking ones. Radial magnets look like this. Yeah, where this is a north pole and this is a south pole. And so what that does is, instead of straight magnetic, so this is what a straight magnetic field would look like. It's straight, right? You got straight lines, parallel lines. What this would look like is you would see this in the middle, but the ones on the outside, they'll curve, right? And so what that ensures is, what that makes sure is that, well, it means that theta is more often 90 degrees. It ensures this right here. And this is maximum torque. Okay? And so how would I answer this question? Well, in words, I would say it ensures that the coil, or in other words, the normal of the coil, I'm just describing theta here, the normal of the coil is always perpendicular to the actual magnetic field. Oh, I shouldn't be writing actual. To the magnetic field. Therefore, it maximizes torque. All right, and that is part D. Let us continue. So this is what we call Faraday's law, isn't it? This is electromagnetic induction, okay? So this is really all about Faraday's law now, okay? So we can just forget motor effect just for a second. All right, and this is electromagnetic induction. We're told that they have a small permanent magnet over here, and it moves into this solenoid to our left here. And at first, in part A, we're asked to indicate on the diagram the direction of the induced current. And remember, we know that there's going to be induced current because this conductor over here, or this solenoid, experiences a change in flux, yeah? So there's going to be a change in flux over time, and we know that that really is just an EMF. And because this is a closed circuit, we know that will lead to an induced current, okay? And now it's asking us, well, what direction is this induced current going to be in? And so really, this is not asking about testing us on Faraday's law, because we already know there's an induced current. The question assumes that they're actually testing us on our knowledge of Lenz's law here. How does Lenz's law play in here? Well, we notice that as the magnet moves towards the solenoid is experiencing an increase in flux, yeah? So let me draw the field lines for a second. This is what the field lines look like. It's experiencing a lot of increase in flux. And we know that Lenz's law, when there's a change in flux, it's going to induce a current to oppose that change. And so it's going to increase, it's going to create flux like this to oppose. Yeah, you see how those arrows are opposing each other? It's going to oppose this north pole coming in. And so really it's going to create its own north pole. It's going to create its own north pole, which I'm going to draw in red over here, to sort of repel, right? That is not the right way, to repel. Yeah? And so how does it create a north pole? We're just going to use our right hand grip rule. So we're going to curl our fingers in the direction of the current and point our thumb in the north pole, right? So if we point our thumb in the north pole, the direction of our fingers is going to be the current, and the current is going to flow like so. It's going to do this, right? That's our current. Okay, I would fill in the whole thing, but I can't be bothered. And so explain the physics reason for this choice. All you need to say is, by Lenz's law, by LL, the current, or rather the induced current, must create flux to oppose the external change. Oh, excuse me. External change in flux, or in other words, create a north pole to repel the external north pole. Now it says in part B, they decided to move the magnet at a constant speed all the way through the coil and then out the other side. Okay, so we see that this magnet is going in, it's going in, it's going in, and then it comes out the other side. So it comes out here, and it's moving at a constant speed here. Okay, it's moving at a constant speed. Okay, so it's just going all the way through here, right? And then it asks us to draw a graph of the current through the coil as time passes. Well, we know that when t is equal to 0, the magnet is actually relatively far away from the solenoid. And so we know that the current is initially going to be 0. But as the magnet moves towards the solenoid, there's going to be a change in flux, isn't it? The conductor is going to experience a change in magnetic flux. Okay, and so there's going to be a current induced, as we already know. Okay, but it doesn't just keep increasing forever. Okay, we know that it has to decrease because when the magnet is traveling at a constant speed inside the solenoid, it actually experiences no change in flux. It experiences no change, right? Because the solenoid is getting used to the magnetic flux that the magnet is creating. And so there's going to be no change in flux for a while, as the magnet is like here, for example. Okay, when the magnet is here, okay, there's going to be no change in flux. Okay, and so here is what we have the the change in flux is equal to 0. Yeah? And then as the magnet leaves, so when the magnet leaves the solenoid, there's also going to be induced current, because then the solenoid experiences a decrease in the flux, right? Because the magnet's leaving. And so therefore, there's going to be an opposite induced current. Okay, so this is when the magnet leaves. And this is when the magnet enters. Okay? And remember, the currents are in opposite directions because the change in flux is opposite. Yeah? And what I mean by opposite, if you think about it, when it enters the solenoid, it's experiencing an increase like this, right? And so it's going to create flux in this direction, in this direction. Let me draw that a bit better. It's going to increase, it's going to create a north pole here. But as it leaves, think about it, as it leaves, okay, the south pole is here. And remember, it doesn't want it to leave. And so it's going to create a north pole here to attract it back. And so the north pole now is in the opposite direction. Okay? And so therefore, the current in the coil is going to reverse. And so that's why we have opposite directions here. Okay, it seems that this is the last question of the first section. So I'm going to finish this question and then pause, and then we'll begin the next section after a short break. So here we've got an aluminium sheet, and it's falling through the uniform magnetic field. And we notice that eddy currents will have to be induced because this is a case of Lenz's law. Okay, and we notice that the magnetic field isn't drawn out for us. So let us draw the magnetic field. So the magnetic field will sort of look like this. Yeah. And so what are the eddy currents going to look like? Well, let's assume that the sheet is actually entering, okay? Because it sort of looks like it's in the middle. So let's say it's actually just entering the magnetic field. When it enters the magnetic field, think about it, it's going to experience a change in flux, isn't it? What is that change in flux? It's going to experience a lot of flux going through it like that, right? Because there's a north pole here. And it doesn't like that, so it's going to create its own north pole in the other direction. Yeah? It's going to create a north pole on the side facing us and a south pole on the side behind it. That we can't see. Okay? And so how does it create a north pole on the side facing us? Well, we're going to put our thumb towards us, right? And then we're going to curl our fingers. And we notice that our fingers curl in an anti-clockwise direction. And so really, the answer here should be B, right? Because it's going to create a north pole that faces us to repel the north pole that's in front of it. Okay, and it's going to create a south pole on the other side to repel the south pole here. And so the answer is actually C. All right. And now, as I said, since we've reached the HSC questions, let us take a break, and we'll be back after this break.